Hello, everyone, and welcome to today's webinar on chamber clean analysis. Our presenters for today are Daniel Sullivan, Account Executive, and Jannica Schneider, Senior Scientist and Project Manager. My name is Vivian Ho, Marketing at EAG Laboratories, a Eurofins company. Before we get started, I'd like to go over a few housekeeping items for today's event. All attendees have been muted. However, we'd still love to hear from you during today's presentation. You will have the opportunity to submit text questions to today's presenters by typing your questions in the questions panel located in the bottom right of your screen. You may send in your questions at any time during the presentation. Monica Newberger, one of our managers at EAG, will be answering some of the questions during the presentation, and we will also collect these and address them during the Q&A session at the end of today's presentation. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. I would now like to introduce our first presenter, Daniel Sullivan, Account Executive at EAG Laboratories.
Hello, Vivian. Thank you very much for the introduction. Sorry, it took me just a second to unmute there. Today we're going to be talking about analysis of environmental chambers, how we're going to determine if they are clean or if they're putting contamination onto our samples. This is me, Dr. Daniel Sullivan. I've been in industry for about 30 years. I did a PhD at UC San Diego and my undergraduate at Berkeley, and there's my phone number and email. Always feel free to reach out and get a hold of me if you have any questions about EAG or any of our capabilities. I do want to introduce Jannica Schneider, and Jannica, can you go ahead and discuss your background?
Hi, everybody. I'm very happy to be here. I am a senior scientist and project manager. I've been at EAG for about 8 years, and I've been working in materials characterization for more than 15 years. I did my postdoc at Berkeley and got my PhD at Santa Barbara, and I specialize in contamination analysis, looking at different kinds of residues and particles and so on, as well as polymer characterization. And I manage projects that involve multiple different techniques, including failure analysis, deformulations, and other kind of metrologies. Thank you, Dan.
Thank you, Jannica. So our outline for today is we're going to go over EAG, sort of tell you about the company a little bit. And then we're going to talk about issues with dirty environmental stress chambers, our test configuration that we used in this particular analysis, and then the techniques that we used. And we used XPS, which looks at the very thin layer of the surface up to maybe 10 nanometers, along with FTIR, which looks significantly deeper up to a micron. And then we didn't use TOF SIMS in this particular analysis, but it is another analysis that makes sense for this if we wanted to go look at the contamination present in greater detail. We'll then discuss the results and go through the conclusion. So EAG is a company that's been around since 1978. We have laboratories in many places in the world. We have 17 laboratories, and we may be going up to 18. I think there's a second one being added in St. Louis, but it's next door to our current lab, so I don't know if that counts. Most of our labs are here in California. You can see we have 3 up in the Bay Area and 2 down south. Let's see. This is our SMART chart, which stands for Spectroscopy and Microanalytical Resolution Tool. So in this chart, you can see the different techniques that we have, and on the right-hand side are the detection limits, and down at the bottom are the area of analysis. So if you have a particular sample that's, say, 10 microns and 1 part per billion, you could then go and figure out that that's supposed to be a TOF SIMS analysis. So this is a very handy chart for sort of figuring out what type of techniques are applicable to your issues. So dirty chambers. So I've actually seen 2 cases myself personally where samples went into a chamber and they came out and they had grown some white fuzz. In those cases, I was the FA guy and I had to figure out, did that material come from the sample itself or was it deposited from the chamber? And so those things can be very, very difficult. And the reason you don't want to have dirty chambers is you don't want false failures where the contamination can cause you issues like opens or shorts, optical blockage, or even just making your part look visually does not look good. So that can be an issue in certain types of samples as well. The shorting and leakage issues can be caused by deposition of conductive materials. The optical path interference is particularly difficult because anything that gets in the optical path of your LED for light output or your sensor for light input will reduce the sensitivity or the output. Opens actually doesn't have to break something in your sample. It can actually just be some sort of non-conducting material that covers the pads that causes the testers later on to have an issue where they get high resistance or they get a non-contact. Also, visual degradation, if you're making parts that have to pass a visual, if they've got some sort of a haze or a film put on them, that won't work very well. Oh, Yannicka, were you going to talk about the sampling kits that we use here and go through the description?
Yep. So we developed a sampling kit to investigate the cleanliness of these chambers. And so it includes a clean silicon wafer, has to be a particular kind of wafer, gloves and instructions. And essentially, you take this kit and you have one of these wafers that is just going to sit in a container and it's going to act as a control. And then you'll have another one that you're going to put inside the chamber. And so then you will do your environmental testing in the chamber for whatever your conditions are. Typically, these run for 1,000 hours or could be longer. And then you will send the kit back to us. We will do optical inspection, and then we'll do some chemical analysis to determine if there's contamination on this wafer, right? And we're always going to have that control wafer to compare to. So in this case, we wanted to do this nice study, and we had 3 different labs that we worked with. So in lab 1, there were 3 ovens that we examined, and we call them chamber A1, A2, and A3. For the other 2 labs, there's just a single oven. And we wanted to have this nice kind of design of experiments so that we could see, are there differences, between the labs? Are there differences between the different ovens in a lab? And all of these samples were tested under the same exact conditions. And of course, we had our reference wafer, the control that didn't see any of this, any of the ovens. And so our conditions in this case were 1,000 hours at 85 C and 85% relative humidity. Now, my understanding is that this is a standard test that is done on these kinds of samples for reliability testing. So this is kind of our analytical process. So first, we want to take pictures and want to see if we actually notice any visible residues. And in fact, we did notice some residues on some of these wafers. The next test we do is infrared analysis. Now that's going to tell us mostly organic information, but also some inorganic, because there are some compounds that, like silicates and nitrates and so on that we can detect. Now, what I want to bring your attention to is something I'm calling the sampling depth and the detection limit. And so the sampling depth here is about a micron, maybe 1,000 to 700 nanometers for FTIR, and the detection limit is 5 to 28%. So this is not a particularly sensitive technique, which is why we also do XPS analysis. Now, XPS will actually tell us a little bit more inorganic information, although it will tell us some organic, right? So these two are very complementary. Now here, we're sampling from a very different volume, right? This is a much more surface sensitive technique. So we're looking at the first 5, 10 nanometers rather than, 700 to 1,000 nanometers. The other thing is this is much more sensitive. So we have much better detection limits with this technique than anything else. Now, the other thing is if we don't detect anything under these conditions, we also have a different technique called TOF SIMS. We'll discuss it a little bit later. It's extremely sensitive. So, it will be useful if you're really looking for very, very minute contamination. But between these two, we should get a good idea, how clean are these ovens? Are they outgassing, and do they have remnants of previous samples that have been in them that might be contaminating, right? So let's look at some images. So this is the images that we acquired from one of the chambers from Lab A1, and you can see that this is the same location on the wafer. If you're using a dark field image, you get a very different kind of optical image than a bright field. So with the dark field, you can sort of see more residues a little bit better. And with the bright field, you can see particles and fibers better. So as I mentioned, once we've done the opticals are very good because they can kind of tell us, do we want to look everywhere on this wafer, or do we want to look at specific locations, right? And so once we've done that, our next step is to do infrared analysis. Infrared analysis is a wonderful method for determining unknown compounds. And so what you do is you irradiate the sample with infrared light, and when you have organic molecules, they are going to absorb that light, and they're going to generate an absorption spectrum. And that absorption spectrum essentially serves as a fingerprint. So it tells us about the molecular structure. So I'll give you an example. Here's an example of a polymer that is a copolymer of acrylonitrile butadiene styrene and acrylic. And so what we can see is in different areas, as I point out, like we have different functional groups. So around 3000, we have aromatics. Around 2900, we have hydrocarbons. Around 2200, we have nitrile functionalities. Around 1700, and so on and so forth. So we can really tell what chemicals, what functional groups are present in these samples using FTIR. Now, there's different ways to do FTIR. ATR measurement, which is a surface-sensitive measurement. You can do grazing angle ATR, which is a surface-sensitive method. In this case, because we have a wafer, which is a very nice substrate for FTIR, we're just going to do transmission, but we're going to do using the microscope. So micro transmission FTIR. All right, so let's take a look at some spectra. So this is a spectra that we see in the first chamber. And you see, this is a pretty so go on. So the first spectrum, or one of the spectra that we see, we characterize as a mixture of organic acid salt, which is the green here. And in addition, we have a silicate, which is blue, right? So already we have identified two compounds here. Another spectrum, again, this is all from the same exact sample. This is from the same chamber. We see a sulfur-containing species, that's in the blue. We see a nitrate, that's in the green. And also the 1695, that's an organic acid, right? So we see an organic acid salt. That's telling us about some pretty significant contamination of that chamber. And as we go through the results, you'll see that chamber A1 was kind of the worst. Here's the last one. This was kind of an interesting finding. We saw some saccharide-looking molecule, which you could sort of see here with the match of all these bands in this region. So that's chamber 1. Now, when we look at chamber 2, or another chamber from lab A, we call it chamber 8. Just that's the number of it. Here, what we detect is a little different. First of all, we see polyamide, that's the green, and that's just probably a skin flake. We see cellulose, that's in the blue here. We also see an ester, 1735, and we see some hydrocarbon oil. Now, I do want to say that these findings, although it seems like there's a lot of stuff, these are actually what we typically see with handling. So aside from probably the ester and the oil, I would say this is actually a fairly clean chamber because we very often see skin flakes just from, these are not kept in a clean room. So skin flakes fall on the wafers very easily. And same thing with fibers from clothing. So with this chamber, our main finding is that we have an ester and maybe some hydrocarbon oil. And looking at chamber 9 from that same lab, again, looks really clean. All we see is another fiber, cellulose fiber. You see that in the blue. And then we have an ester, 1729, and then an amide, 1664. Here. Okay. And then this one also had a skin flake, right? So again, the theme is when we see skin flakes, when we see cellulose, those are just probably from handling, and they're not necessarily something that's wrong. The next thing is we have the next lab. So this is chamber B1. So this is from a different lab. And what we see here is fluorosilicate glass. So maybe there's something that's happened with the wafer. It was heated. Maybe a little bit of oxide came on the surface. And then the peak at 620 is due to an amide. Now with third lab, this is our third one. This one actually did appear to be quite a bit more contaminated. So here we have a couple of things that we see. So first of all, we see the ammonium, and this is actually a pretty strong signal for ammonium, some kind of ammonium salt, right? Especially with these particular peaks and the 1414. The other thing we see is possibly some kind of sulfate compound. And then finally, what's very important is this organic acid at 1720. Right? And then also in this one, we saw skin. The other thing it's kind of hard to see, but there is this tiny little peak at 1628. Again, that could be due to an amide or maybe some aromatic. All right, so let's put all this data together. Chamber A, we saw organic acid, maybe sulfur species, maybe nitrate, saccharide, some candy or something. Chamber A8 and A9 from the same lab, just a different chamber, were quite clean. B1, at least by FTIR standards, was fairly clean. Silicate, we often see that, and these are subject to damp heat, so there could be some small transformation to the wafer, but we do see some amides in a lot of these, and those could potentially be problematic. Now, in chamber C1, we also saw a trace organic acid. That could be very problematic for electronics. And then, the amide, ammonium, that could also be quite problematic. So overall, with respect to FTIR, we saw that chamber A1 as well as C1 were quite contaminated. So, and then the ones that are sort of purple, those ones are probably just some kind of handling contamination. So we would consider. And now I believe the next part is XPS. So I will turn it back over to you, Dan.
Thank you, Yannicka. So I'm going to go through the XPS surface analysis right now. The XPS tool we uses a monochromatic aluminum K alpha source to radiate the sample, and we look at the electrons that are come off the surface. It's very surface sensitive, so as opposed to the IR, which looks moderately deeply into the sample, we're looking just at the very surface to get the elemental composition, except for hydrogen and helium, which we can't see. And in the high-res scans, we can get some chemical information. So we did both survey scans and high-resolution scans to get the elemental composition and the chemical state information. And down below, there is a separate webinar that we've done in the past on XPS, and that's the link to it if you want to watch that webinar. All right, so the process is we put a sample into our vacuum chamber and we irradiate with an X-ray. And then the photoelectrons come out. And the reason that we have such surface sensitivity is we only are interested in the electrons that escape without having an energy losing collision. So that limits it to about maybe twice the mean free path of the electron, which is why we get this surface sensitivity. So this is a result on our chamber A1, which was the most interesting one from the XPS. Our reference silicon wafer has silicon, carbon, oxygen. The carbon and oxygen you'll wind up on almost every sample once you expose them to air. The chamber A1 actually had residues of tin and zinc on the surface. So having tin and zinc floating around in your chamber are not good. So this was actually very surprising to us, but this was something we wanted to let them know. This is actually on a chamber where they had been doing some adhesive work in the past, and they wanted to know if they could then use this as a reliability test chamber. And based on the zinc and the tin alone, I would tell them they need to have a good cleaning before they start doing that. So chambers B1 and C1, which were in the other laboratories, have also some things that we see in the XPS that are not present on the reference chamber. The chamber B1 has a strong sodium peak. You can see that out here. There's a very large sodium peak along with a chlorine peak. And sodium and chlorine, along with a much larger carbon peak, scream of handling, right? That's somebody's fingerprint. So that's what's going on in chamber B1. It probably has some handling issues there. And that may be handling of the wafer by the person putting it in and out of the chamber, or it could be from the chamber itself, just needs some cleaning to get rid of sort of the human residue. In chamber 1C, we see this little nitrogen peak here that popped up that might be the amines that the FTIR have been looking at. Other than that, it looks fairly similar to the reference chamber, so it looks fairly clean except for the nitrogen peak. Now, these are high resolution scans, so we can take a scan like these, where we're going from 0 to about 1300 EV for binding energy. Then what we can do is we can go down to a much smaller scan. Say for the carbon 1s up here, we're going to go from 280 to 292. And this scan allows us to get much more resolution on the data. And we can see where we have here for the control, we see we have very little carbon here. But on the B1, we actually see we have a large hydrocarbon peak, a small carbon bound to oxygen, and a small but significant carbon doubly bound and singly bound here. So we can differentiate these types of carbon. And in chamber C1, you can see we just have a little hydrocarbon. And we can do this for each of the different types of elements we want. Here we're looking at the oxygen, here's the nitrogen. The silicon, you can see that there's a silicon metal and then there's SiO2. And you can see these are present in the other chambers as well. And so for something like the sodium, if it was a small peak, we could actually go into these binding range here and, for instance, run at a longer period of time over this smaller area and detect trace amounts of the chlorine, for instance. So this is the summary of the XPS results. And I just wanted to show that the control chamber is similar to most of these in carbon content, except for B1. B1 has a lot more hydrocarbon here. And then the other chamber here, A1, I want to call out, this is the zinc and the tin, which are very concerning. And then in chamber B1 and C1, we actually had a little bit of the nitrogen. And then we also have the sodium and chlorine here seen on B1. So these are all the things that we wind up seeing. Everything else that has a dash there basically means it's below the detection limits. So in this way, we can immediately call out this chamber B1 for some sort of a contamination from handling. And chamber A1, we can see that there's these concerning elements of zinc and tin. So this is a comparison chart for the FTIR and the XPS. And this basically just goes through the things we had talked about. And Monica had done the FTIR summaries earlier, and the XPS results are the ones I've just gone over here as well. And so we can see these types of things fairly easily with these two techniques and call out the possible contaminations that would be of concern. So TOF sims we didn't do in this case because we saw stuff right away. TOF sims, the time of flight secondary ion mass spectroscopy, looks at elements and molecular fragments from the matrix and it's also very surface sensitive. It's 1 to 3 nanometers. And what it is, we would directly compare our results to a control in order to see if, say, amines are present. Now, in the case where you see some sort of gross contamination like we did on some of these, the TOF sims may not be necessary. But say you saw a fairly clean sample, but you are extremely sensitive to any contamination, you may want to do TOF sims to go see if there's a more trace contamination. Or if you were very, very concerned about the amines that we saw in the FTIR and the nitrogen we saw in the XPS, and you want to know more about that molecular structure, we could go and use TOF sims to look at that. Again, there's also been a webinar done on TOF sims, and there's the link right there. You're welcome to go and look at that webinar as well if that's of interest to you. This is a link to our paper. We just wrote the paper that we based this webinar on. It's up on our website, and there's the link to it. Feel free to go take a look at it and have a read. And then I did want to go over why would you choose EAG to work with. One is our client confidentiality is core to our business. In this particular case, we did look at some chambers for customers. We got an agreement in writing with them to be able to publish this information and not disclose who they are. So the confidentiality of our customers is very important to us. We have extensive knowledge base and many skilled people here. We have a multidisciplinary approach to support you. One of the things that's very nice is we have, I think it's 200 or 300 different analysis we do, and we have 2,500 instruments to do that worldwide. We're also a worldwide leader in materials testing and have been around since the 70s. And we have our ISO 9001 and 17025 accreditations. And we're willing to help you and talk to you about any type of materials or engineering problems you might have. And you're welcome to contact any of us to discuss those types of issues.